Okay, so let's continue our look at relativity. First of all, a bit of a reminder, we've actually discussed the idea that there's been lots of experiments to confirm the speed of light staying the same and in different frames. So the speed of light is a constant, and they know what that is, no matter what the reference frame is. And that's been done to high precision over a long period of time. The other thing to bear in mind is this idea of length contraction and time dilation. If you have a carriage there, and we said the outside observer would see this particular event where they shot a beam down there and backwards again, as different if the cart was moving at high speeds. The person inside sees it goes like this. The person outside sees more of this motion going on, doesn't it? Now, this can actually sort of be brought back into that line with the other person's reference frame if you consider the idea that the actual carriage itself in that direction shrinks in the direction of the velocity there, so length is contracted that way, and it's actually made a longer time. And that kind of brings around more like to that, with a longer time period and a shorter length. It brings that more straightened up to be in line with the other reference frame. Okay, so just something to keep in mind. You get length contraction and time dilation by that Lorentz factor. All right, so let's look at some other evidence we've got here for this. All right, so let's look at the effect of muon decay. So muons are small subatomic particles, which is a type of lepton, which we're going to look at when we do the standard model near the end of the course at the end of term 3. So they have got relativistic effects, and there's good examples or evidence of relativity. Muons are small subatomic particles that can be reduced in a lab. They've been measured with at low speeds in the lab to have a half-life of about 2.2 by 10 to the minus 6 seconds, or 2.2 microseconds. Now that means that after one of these half-lives pass, you're down to half the amount being there, the other half have decayed. After another half-life, you're down to a quarter, so it's a half of a half, and then you go down to an eighth and so on, which we did last year. So, they're also created though in the upper atmosphere at high speeds of 0.99 the speed of light. And that happens when cosmic rays hit the nitrogen nuclei or the oxygen nuclei in the upper atmosphere, so up here. And they've got about 10 k's to travel there to actually reach the Earth, the ones going in that direction. Without the relativity effects or the relativistic effects, you should find that they will not reach the Earth's surface because 0.99 times the speed of light times by the time they've got for a half-life, they're only going to travel about 650 metres before a half-life passes. And then another 650 metres before another half-life passes, you're down to a quarter. And if you keep on going, you get to over 15 half-lives. It's a very tiny fraction of muons are reaching the surface. When they've measured this and compared it at one high atmospheric point to the low one near the Earth, the difference is not as big as that. Okay, you're roughly just below a quarter. So how can this be explained? The other way of looking at this is the time for a muon to travel the full distance to the Earth, to reach the Earth completely, it would be T over S, where S is the distance to the Earth through the atmosphere, and that's 10 kilometres, 10 by 10 to the 3. Travelling at that speed of light, it should take this many seconds, which again is a long time in terms of half-lives. So you can look at it by distance point of view, or time point of view, if you don't take relativity into account. So, how does this give evidence of relativity? And that's what I've just said there, it's about 15.5 half-lives. The reality is that a significant number have been recorded as reaching the Earth's surface compared to the atmosphere, much more than you would get if your relativity was not taken into account. So let's have a quick look at why there. So the time for the muon to reach the Earth's surface for an observer in the frame of reference of the Earth here is going to be dilated. We're going to see it as a longer time for the muon to travel down to the Earth's surface. If you want to work out how much, you do the gamma factor, the Lorentz factor. And you work it out as 1 subtract 0.99 the speed of light over c all squared, and you end up with 7.1 times longer. So time is dilated by 7.1 times, okay, from our point of view, watching the muon come down. And that actually is consistent with the results, by the way, okay? So when you go and check it out, you get a time of 15.6 by 10 to the minus 6 instead of the other one, which is only a couple of half-lives, just over 2, all right? So we get just under a quarter reaching us, and that's consistent with the evidence we're getting experimentally. So it's good evidence of relativity here. Now there's another way of looking at this. If you think of it from the muon's point of view, something happens we haven't considered yet. And that is that from the muon's point of view, the actual Earth is coming towards it at that 0.99 c. Okay, 0.99 the speed of light. So it's going to see relativity going on from its rate of reference in terms of length contraction. It will actually see the length of the Earth, the distance from the atmosphere to the Earth's surface, to be shorter than what it really is compared to the people on ground. So this length contraction from the atmosphere would give you the same sort of result if you consider the same gamma result, because it will be the same. From the muon's reference frame, you're going to get a shorter length there with this sort of factor here. So checking that out, the length of the atmosphere according to the muon travelling towards the Earth, or the Earth travelling towards the muon from their reference frame, is going to be L naught divided by gamma, And you get 1.4 kilometres. It's shortened down from 10. So as far as it's concerned, it's just travelling a shorter distance and it makes it. And again, if you check that out, 1.4 kilometres divided by 650 metres it's got as a half-life. Would be 2.2 half-lives. And again, you get just under a quarter getting there. So that's more another way of looking at that. So this is consistent with the stuff of relativity here that we've been doing. So lastly, I just want to look at this idea of simultaneity, which we discussed earlier, but I forgot to put up in the notes here. So events are simultaneous if they happen at the same time, okay? But simultaneous events are not necessarily simultaneous to all observers. So a simultaneous event might look simultaneous to you, but different in a different frame of reference. So for example, if you had a person in the middle of the carriage here, and they shone a light beam in two directions off mirrors, okay, inside the carriage they would actually see, or the girl would see the light reach each end at the same time, okay, and actually returns at the same time to her. But if you're watching from outside here, from this observer's point of view, you would actually see the light beams go out, but don't forget the carriage is moving that way, and if it was moving at high speed like v equals 0.8 c, you'd notice that this is coming towards it, so the distance travelled by the beam here should be shorter, and this will actually hit this mirror first. So you'd see the same event, simultaneous, not occur simultaneous for your reference frame. This would occur first, and that would occur a fraction of a time later. The outside carriage there is going to see the back of the carriage is where the beam hits first, okay? Because the carriage has been moving towards that beam. So time is not an absolute quantity when you're talking about relativity. All right? Okay, thank you.